Over 1,000 years before calculus was invented, a mathematician in Syracuse had already calculated the area under a curve. He didn't call it calculus. He didn't even have the notation. But the answer was correct. 4,000 years ago, in a civilization that hadn't invented the concept of zero yet, scribes in Babylon were solving quadratic equations. Not approximately. Exactly. We know this because of clay tablets. Thousands of them, baked into permanence by accident when ancient cities burned. When scholars finally translated them in the 20th century, they found something that stopped them cold. A step-by-step algebraic method for solving second-degree equations, written around 1800 BCE. The tablets describe problems like this. A field has an area of 55 square units, and its length exceeds its width by 6. Find the dimensions. That's a quadratic. And the Babylonian scribe solves it using what we now call completing the square, a technique taught in modern high school algebra. Here's what makes this genuinely strange. The Babylonians had no algebraic symbols. No x, no y, no equals sign. They wrote everything in words. Long, careful sentences describing each arithmetic step. But the logic underneath those sentences is structurally identical to what a student does today with a pencil and a formula sheet. They weren't guessing. They weren't estimating. They were operating with a full procedural understanding of how quadratic relationships behave. Scholars initially assumed these tablets were just accounting records, land surveys, grain ratios, tax calculations. And some were. But others were purely abstract. Problems with no real-world application, constructed specifically to practice and teach the method. That means someone, 4,000 years ago, was doing mathematics for the sake of mathematics. Not to build something. Not to measure something. Just to understand how numbers work. The Babylonian number system was base 60, which is why we still have 60 seconds in a minute and 360 degrees in a circle. That's not coincidence. That's inheritance. We are still using their arithmetic right now, every time we check a clock. In 1906, a historian named Johann Heiberg traveled to Constantinople to examine a damaged manuscript in a library. The parchment had been scraped and reused, a common medieval practice called a palimpsest. Underneath the prayers written on top, Heiberg could make out older text. Greek text. It turned out to be a copy of a work by Archimedes that no one knew had survived. The manuscript was called the Method, and it contained something extraordinary. Archimedes, working in the 3rd century BC, had developed a technique for calculating areas and volumes that involved mentally slicing shapes into infinitely thin sections, weighing them against each other conceptually, and using the comparison to deduce exact measurements. He was using the core intuition of integral calculus, nearly 2,000 years before Newton and Leibniz formalized it. He calculated the area of a parabolic segment. He found the volume of a sphere. He worked out the surface area of curved shapes that no one had touched before him. And his answers were exact, not approximations. But here's where it gets interesting. Archimedes himself didn't fully trust his own method. He used it to discover results, then went back and proved them rigorously using a separate technique called the method of exhaustion, essentially constructing formal proofs that didn't rely on the infinity slicing intuition. He knew the method worked. He didn't know why it worked. And that uncertainty apparently bothered him enough that he kept the two approaches separate. The method manuscript was lost again after Heiberg examined it. It resurfaced at a Christie's auction in 1998, sold for $2 million, and is now in Baltimore. Imaging technology has since revealed even more of the text. Mathematicians are still studying it. Archimedes had tools in his mind that the rest of the world wouldn't rediscover for nearly 20 centuries. That's not an exaggeration. That's just what happened. In the 14th century, in the Kerala region of southern India, a mathematician named Madhava wrote down something that Europe wouldn't figure out for another 300 years. He expressed pi as an infinite series, an endless sum of fractions that converges, term by term, toward the exact value of pi. The series runs forever, 4 minus 4/3 plus 4/5 minus 4/7, and so on, alternating, each term bringing the total closer to pi. Today this is called the Leibniz formula for pi. Leibniz published it in 1676. Madhava wrote it down around 1360. But Madhava didn't stop there. He also derived infinite series for sine and cosine, the same series that appear in every modern calculus textbook. He understood how these series converge. He developed correction terms to make them more accurate with fewer calculations. He was, by any reasonable measure, doing the work of early calculus. The careless school of mathematics that Madhava founded continued for over a century after his death. His students and their students kept developing these ideas, refining them, pushing further. Then, essentially, the transmission stopped. The work was written in Malayalam, in verse form, mathematical results encoded as Sanskrit-style poetry, a mnemonic tradition that made them memorable but also made them inaccessible to anyone outside that specific scholarly lineage. Whether European mathematicians of the 17th century somehow received indirect knowledge of Kerala's work is a question historians still argue about. There were trade routes. There were Jesuit missionaries moving through the region. The timing is suggestive. But there's no direct evidence of transmission, so the official history still credits Newton and Leibniz with the invention of calculus. Madhava's name appears in footnotes, if it appears at all. For most of history, his work sat in manuscripts no one outside Kerala was reading, describing mathematical structures the rest of the world was centuries away from finding on their own. Around 240 BC, a man named Eratosthenes, working as the head of the Library of Alexandria, calculated the circumference of the Earth. He didn't have satellites. He didn't have aircraft. He had geometry, one well-placed observation, and an almost uncomfortable amount of mathematical confidence. Here's what he knew. On a specific day each year, in the city of Syene, roughly modern-day Aswan in Egypt, the sun shone directly down a deep well at noon. Perfectly vertical. No shadow. At the same moment, in Alexandria, which was north of Syene, a vertical stick did cast a shadow. The angle of that shadow was about 7 degrees. 7 degrees is roughly 1/50th of a full circle. Eratosthenes knew the approximate distance between Alexandria and Syene. Multiply that distance by 50, and you have the circumference of the Earth. His answer, converted into modern units, was somewhere between 39,000 and 46,000 kilometers, depending on which ancient unit of measurement he was actually using. Historians still debate this. The actual circumference is about 40,075 kilometers. He was, by most interpretations, within a few percent of correct, using a stick, and a well, and geometry. What's remarkable isn't just the accuracy, it's the conceptual leap. Eratosthenes didn't just measure the Earth, he understood that the Earth was measurable, that its physical dimensions were accessible to human reasoning without leaving the ground, that mathematics could reach out past the directly observable and return with facts about the world. That is not an obvious idea. Most people in most eras have assumed that certain things are simply beyond knowing. Eratosthenes decided they weren't. And he turned out to be right in ways that extended far beyond one afternoon with a shadow and a piece of paper. A stick, a clay tablet, a scraped manuscript, a verse written in Malayalam. The tools were modest. The ideas inside them were not. If you want more stories like this, subscribe. There are plenty of them.